This video is going to go over a voltage or potential difference problem. An electron is accelerated by a uniform electric field of 1000 volts per meter pointing vertically upwards. Use energy methods to determine the electron's velocity after it moves 0.1 centimeters from rest. Okay, a couple of things I want to mention here. First, let me just sort of quickly draw the electric field. Okay, there it is, pointing vertically upwards, and it has a magnitude of 1000 volts per meter. We've learned previously that the unit of an electric field was newtons per coulomb. So now you're seeing volts per meter. Well, they're equivalent. This is the same as 1000 newtons per coulomb. Now, a 1 volt per meter and 1 newton per coulomb are exactly the same. And the reason they do this is depending on the industry that you're in or the research you're doing, it is sometimes easier to use volts per meter than newtons per coulomb. They're exactly the same thing. Now, one other thing. The electron is going to be placed in this electric field, which is going to move. Now, initially, and you would be correct, you'd think, hey, the electron has mass. It's going to feel a force of gravity downwards. Do we have to take that into account? And in this case, we are going to ignore gravity. And you may say, hey, why can we ignore gravity in this case? Well, Fg is equal to the mass times 9.81 meters per second squared. But the mass of the electron, which I probably should have put in the problem, but it's easy enough to look up, is 9.11 times 10 to the negative 31 kilograms. So if you were just to multiply that by 9.81, basically you're getting a force of gravity that's somewhere in the region of 10 to the minus 30 newtons, which is so small compared to the other forces acting on the electron that we can just call it negligible. It's not going to have a huge impact. The electron is so tiny and so little mass that gravity is not going to be an issue here. So if I put the electron in the electric field, one of the things to note is that an electron, a negative or any negative charge, when it's put into an electric field, is going to feel a force that's in the opposite direction of the electric field. In other words, the electron is going to move or feel a net force in this direction. So initially, it's at rest. And then it will move a distance of 0.1 centimeters downwards. And we would like to know what its final velocity is right here. So how can we go about doing that? Okay, so one way to do it is to use the conservation of energy. So we have the initial kinetic energy, plus we're going to ignore the gravitational energy because, as I said, we're going to ignore gravity. So this is going to be the electric potential energy, plus any non-conservative other forces will equal to be K final plus UE final. Now, we're not worried about friction. And as I said, we're not going to worry about MGY because we're going to ignore the effect of gravity here. And it turns out the electric force is a conservative force and it's related to the potential energy. This is zero. There are no other forces interfering with the electron. So this is zero because we start at rest. Here's what we're going to do. We know that this is going to be Q V naught. This is going to be 1/2 mv final squared plus q v final, or just write it like this. So this is going to equal negative q delta v. Why is there a negative suddenly in front of that? It's because of this. Remember, q delta v is v final minus v initial, because this is equal to the negative delta v. Okay, so remember that delta v is equal to the electric field times the distance. I'm just pausing it right here to give a little point of clarification. What I've just shown you is the formula for delta V is equal to the electric field magnitude times the distance of displacement. Now, what I'm about to write next, though, is not delta V. It's going to be the negative Q delta V part from the previous equation. So I just wanted to avoid that confusion because I didn't like the way it looked when I was reviewing it. So what this is going to be is Q is negative 0.6 times 10 to the negative 19 coulombs. E is 1000 newtons per coulomb. D is 0.001 meters. That's going to equal 1/2. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. Sorry, I ran out of room there, so I just quickly adjusted it. This will be V final squared. So at this point, these two negatives are going to cancel each other out. We can just go ahead and solve for VF. And VF turns out to have a magnitude of 5.93 times 10 to the 5th meters per second. But in order to get its own sort of velocity, we have to include a direction. So this is going to be 5.93 times 10 to the 5th meters per second downwards. All right, this was a complicated problem, so go slowly as you look through this one, and please come see me if you have any questions. Other than that, thank you for watching, and have a great day.